Welcome to the topics in section 2.8. We're going to look at the derivative as a function. We're going to look at this in 5 different parts. We're going to look at the definition. We're going to look at notations for the derivative. We're then also going to explore what is the differentiability of a function. Is it differentiable everywhere? And then we're going to look at the contrapositive of that theorem. And then we're going to look at higher derivatives. Let's go. First part, definition. In our previous section, we found that the derivative of a function at number a, if we replace the a with x in definition 1, we now have the definition for the derivative of a function. In other words, the derivative of f, denoted by f prime of x, is a function obtained from f by this formula. That formula should start to look familiar by now, right? Whether we're doing it with a or whether we're doing it with x, that should start to look familiar. The domain of f prime of x, that's the domain of the derivative, exists as long as that x value works for the derivative. So in other words, the domain of the derivative may be smaller than the domain of the original function. It may not be the same. Let's do an example. For each of the following functions, let's find f prime and then state the domain of f prime. Okay, we just did this one. So let's just show quickly how we can find it again. Remember, we're going to do f of x plus h minus f of x all over h. Let's plug that into the function. Remember, f of x is the original function. F of x plus h is the original function where we're plugging in x plus h for x. That is my 1, 2, 3, 4, 5th orange marker. I said last time I wasn't going to use the markers anymore, but let's see. Ooh, oh, that's a different orange. Let's see how long this one lasts. Okie dokie. So I'm going to cube this. And I'm going to distribute the -4. And then I'm going to subtract f of x. The regular f of x. Oh, forgot my limit thing again. Thinking about changing markers. Now, let's simplify. If I distribute this out here, the negative sign, I'm going to have negative x cubed and a positive 4x. When I combine like terms, I'm going to notice that my x cubed cancels and my 4x cancels. And what I'm left with is my 3x squared h plus 3x h squared plus h cubed minus 4h all over h. It should look familiar. We just did it in the previous section. Don't worry, we have more examples. Now let's cancel that power of h. I'm going to show it a little bit differently. I'm going to factor the h out. Remember, this is creative freedom. You can either factor it out like this, or you can factor it out the way I did the last time I worked on this problem. But either way, 1 power of h should be taken out of each piece of the top. And then these h's cancel. And I'm left with 3x squared plus 3xh plus h squared minus 4. And then I'm going to plug in h equals 0. That makes this go to 0 and this go to 0, which gives me f prime of x is equal to 3x squared minus 4. Let's try another. Next function, let's find the derivative for f of x equals the square root of x. So keep in mind our formula. I'll write it down here. Now this will give us f prime of x is going to be equal to the limit, as h approaches 0, of f of x plus h minus f of x all over h. Keep in mind that f of x is just the original function, and f of x plus h is when I take x plus h and I plug it into the function for the spots that have the plane Jane x. All right, let's simplify. So I've got the limit as h approaches 0 of f of x plus h, which is this function, minus f of x all over h. Now, if I evaluate this as h equals 0 now, I would end up with 0 over 0, which means I have work to do to see if I can get it to exist. So I'm going to do the limit as h approaches 0. Actually, sorry, before I write that, I'm going to use one of my math smoke and mirror tricks. I am going to multiply by the conjugate. I'm going to multiply by the conjugate of this one. So I'm going to multiply by that. But because I have to make it a legal math move, I need to multiply the whole fraction by that. Okay, so I'm going to multiply the top and the bottom of the fraction by the square root of x plus h plus the square root of x. Remember what happens when you multiply these out. You get a difference of squares. So you end up with x plus h minus x all over h times that square root of x plus h plus the square root of x. And nothing magical happens at the denominator, at least not yet. If we simplify the top, notice what happens. Yeah, everything with an h goes by. So x minus x, those cancel. And we're just left with the limit as h approaches 0 of h all over h times the square root of x plus h minus the square root of x. Note, don't multiply stuff out in the denominator, at least not in the beginning. Oftentimes we don't need to, and it's just a waste of time. Leave the denominator written in pieces instead of multiplied together, because if anything can cancel, you want it to be listed in pieces. And I said that for a specific reason, because notice, the h's will cancel. Now, avoid a common pitfall. What's the common pitfall? Yeah. Don't forget that everything in the numerator canceled. Since everything in the numerator canceled, that means you're going to be left with 1 on the top. In the denominator, you're going to be left with your square root of x plus h. Sorry, that's a plus, plus the square root of x. Once you've got something to cancel, plug in your h value again of h equals 0, and let's see what happens. Yeah, we plug in this, and we end up with, equals 1 over the square root of x plus 0 plus the square root of x. Well, the square root of x plus 0 is just square root of x. So f prime of x is going to give us 1 over 2 square roots of x. And that ends up being our final answer. Let's try another. Think of this as letter C. This is a bonus problem. I want you to find the function for the derivative for this rational function of 1 minus x divided by 2 plus x. This one's really tricky and very long, so make sure to use pause and rewind as you need to. Remember, we are going to use this formula. The limit as h approaches 0 of f of x plus h minus f of x all over h. It would be helpful as we get started to remember that f of x is the original function. F of x plus h is the original function where every instance of x is populated with x plus h. So that creates this new function. Let's see what happens. So for f of x plus h, I have this fraction. And I'm going to subtract from it this fraction. And that whole thing is over h. If I plug in the h equals 0, I've got this pesky h in the denominator that's going to cause problems. So I have to do some math smoke and mirrors. I don't know if you remember from a few sections ago, the last time we played with fractions, but what we're going to do is use the trick of multiplying through by the LCD. The LCD for this is this denominator right here. So I'm going to multiply by 2 plus x plus h. And I'm going to multiply the top and the bottom by that. And I'm going to multiply by this denominator, 2 plus x. And I'm going to see what happens. Notice that when I multiply the denominator, life is super easy. It's just h times this chunk of algebra. And leave that denominator alone. Don't try to simplify the denominator. We want things to cancel. Leave it as it is. The math stuff that we're going to do, the arduous math stuff that we're going to do, is always in the numerator up here. Okay, so now what I'm going to do is I'm going to multiply this whole thing. I'm going to multiply this whole thing by this fraction and this fraction. When I do, watch what happens. So much writing. Oops. Can you see that? You can't see that. Get rid of that. Okay, again, notice what I've done, and I want to have a line here. Kind of keep things separate. So I'm getting crowded. What's going to happen? Over here, notice this 2 plus x plus h is going to cancel with this 2 plus x plus h. So this one and this one's going to cancel. And I'm going to be left with this numerator here of 1 minus x plus h. and that's going to multiply by 2 plus x. Over here for this fraction, when I multiplied out the LCD, the 2 plus x's cancel with each other. And then the numerator of 1 minus x is going to be multiplied by what's left over here, the 2 plus x plus h. And then the denominator is just that simple thing that I'm not going to modify at all until the end, really. Okay, this is where I want to simplify a little bit. What I'm going to do is I'm just going to distribute out the negative sign here. And then what I'm going to do is I'm going to take this minus sign and I'm going to plug it into this to turn it into x minus 1. You don't have to do it. It just makes it easier to simplify. So this becomes plus, this becomes x minus 1. And this becomes minus x minus h. Oh, and I want to get rid of these parentheses here, because I got to do all the simplification in the top. I'm a little worried I don't have space. Okay, so the bottom is just, it's just the bottom. It's just going to go along for the ride. Nothing's going to happen to it. I'm going to write that last. I want to make sure I have room for the top. On the top, what I'm going to do is multiply this out. When I multiply this out, I always start with the chunk of algebra that has the least amount of terms. This is a binomial. This is a trinomial. So I'm going to multiply the binomial by the trinomial. In other words, I'm going to take the 2, and I'm going to multiply it, and then I'm going to take the x, and then I'm going to multiply it. So multiplying the 2 out, I'm going to end up with 2 minus 2x minus 2h. Then I'm going to multiply the x out. So x times 1, x times negative x, x times negative h. I'm going to run out of room. Darn it. Okay, I'm going to do the same thing over here. I'm going to multiply the binomial out to the trinomial. So I'm going to multiply the x out first. And notice that's why I changed it to plus, so it would be easier. You can't see it. Dang it. I'm going to come up here. And then I'm going to multiply by negative 1. So this gives me a minus 2, a minus x, and a minus h. And that's all over this denominator here. Again, remember, I don't do anything with that denominator. Okay, so I'm going to get stuff to cancel. Notice a couple things. The 2's cancel. 2 and negative 2 cancel. I've got minus 2x and a plus 2x. That cancels. I've got minus 2h and minus another h. So that's going to combine on the top. I'm going to come down here to give me a minus 3h. So this minus 2h combines with this minus h to give me a minus 3h. This plus x cancels with this negative x, and this minus x squared cancels with this x squared, and then this minus xh cancels with this minus xh, and then that's all I have left in the numerator. See, all this hard work pays off. All that stuff just to get a minus 3h. All right, now in the denominator, I've got that thing I still haven't touched. It's just going along for the ride. It's a little hitchhiker. And then what happens is I get something really cool. See this? I got an h up here and an h down here. This is why I didn't factor them. This h and this h, those things will cancel each other. Poof, gone. And then I end up with And now that pesky h in the bottom is gone, now I can plug in h equals 0 and evaluate my limit. When I plug in h equals 0, that becomes 0. And I end up with negative 3 over this, which simplifies to this. So warm in this room. All right. That's f prime of x for that problem. Okay, after all that work, this function right here is my f prime of x for this f of x right here. There are a ton of steps to this problem, and actually it's really easy to mess up. All you have to do is forget to cancel something, or forget to combine something, or forget to distribute a sign correctly, and there's a lot of potential for error. So keep your wits about you. Don't get frazzled. Do each problem a couple of times, and then always check your work. You don't have to do it perfect every time. You just have to be good at catching your mistakes. That's what makes you a successful math student. All right, I hope this was helpful. Next part of section 2.8, notations for derivative. We have quite a few of notations for derivative, and it just kind of depends on which one you like or which one is used for a particular type of problem. But if I want to find the derivative of f, I can use this notation, which we've already seen, f prime of x. I can use this, y prime, or I can use dy dx, df dx, or d dx of f of x, or capital D of f of x, or capital D sub x of f of x. Those are all the different notations that we have for the derivative. So for example, if I'm trying to find the derivative of this function here, I can call the derivative y prime. I can call it f prime of x. I can call it dy dx. I can call it d dx of f of x. I can call it capital D of f of x, or d with respect to x of f of x. And I could also write it like this. I could say the derivative of that function and just write that function in there. Many ways to write a derivative. The derivative of a function can only be found if it is differentiable at that point. So a function f is differentiable at a if f prime of a exists. It also is differentiable on the open interval of a to b if it is differentiable at every number in that interval. Basically, it takes us to this theorem. If f is differentiable at x equals a, then f is continuous at x equals a. Note, this theorem does not say that if f is continuous, then f is differentiable. The idea is this: if it's differentiable at that point, then it's continuous at that point. So let's take a look at what that means. So here, I'm looking at this function f of x being the absolute value of x. If you remember from a previous lecture, we were defining absolute value functions as piecewise functions. Okay, so the absolute value function looks like a v, which are the two lines, negative x and x, combined together. Negative x when x is less than or equal to 0, positive x when x is greater than or equal to 0. First part, is the function of f continuous at x equals 0? Well, we got to do that 3-piece, right? We got to do the 3 steps. First of all, we got to look. Is f of 0 defined? And that's a yup. It is defined. When x equals 0, you get negative x. So it is defined. You can take the absolute value of 0. That gives you 0. Next. Does the limit as x approaches 0 of f of x exist? Remember, if it exists, we have to look at the left-hand side and the right-hand side. So the left-hand side, let's look at this. The limit as x approaches 0 from the left, we use that little minus sign, of the absolute value of x. Well, approaching 0 from the left uses that top row. This is like saying the limit as x approaches 0 from the left of negative x. Well, we can plug in 0. Negative 0 gives me 0. All right. That's my left-hand side. Let's see what the right-hand side looks like. So the limit as x approaches 0 from the right-hand side, we use that little plus sign, of the absolute value of x. The right-hand side of the function is part of that v, okay, part of that v. That's this side of that absolute value function. That's that second row. So this is the limit as x approaches 0 from the positive of positive x. Well, if we plug 0 into there, we get 0. Cool. Those are the same. So this limit does exist. It does. And it's equal to 0. Our third step of continuity, let's just take it right here. Can I squeeze it in here? Yeah. Basically, we look, does number 1, the result from number 1 equal number 2? Yeah. F of 0 equals the limit as x approaches 0 of f of x. This is a yup as well. So is it continuous? Yeah. It is continuous. But is f differentiable at x equals 0? So, let's see. If we were to do the limit as h approaches 0 of f of x plus h minus f of x all over h. Let's take a look at what happens. I need to give myself some more room. It's going to take some time. Okay, so let's look at this limit. Now again, keep in mind, if we want to find the limit to see if it exists, what we're going to do is we're going to use the left-hand side limit and the right-hand side limit. So the left-hand side limit is the limit as h approaches 0 from the left. And so we're going to do that as the absolute value of x plus h is subtracted by the absolute value of x all over h. Now remember how the absolute value function looks. It looks like that v. Okay, the left side is that negative. So this would be the limit as h approaches 0 of negative x plus h minus a negative x all over h. And again, that left-hand side is that negative. That's that v. Remember what the absolute value looks like. There's a line with a negative slope, line with a positive slope. Now, let's go ahead and evaluate that. So distributing the signs, I'm going to get a negative x minus h plus, because these two minuses will make a plus, x. So the x's cancel. but I'm left with a negative h in my numerator. And then when I cancel that, I end up with the limit as h approaches 0. I wrote the plus here, minus for negative 1. Okie dokie. So the left-hand side, the derivative is going to give me negative 1. Let's look at the right-hand side. So the limit as h approaches 0 from the right of the absolute value of x plus h minus the absolute value of x all over h. For the right-hand side, this is the one with the positive slope. So the absolute value of x plus h is the same as saying just the regular inside, x plus h. And then minus the absolute value of x. The absolute value of x is positive x for that right-hand side. Again, the x's cancel, and I'm left with the limit as h approaches 0 of h over h, which is the limit as h approaches 0 of 1, which is simply equal to 1. And that's my right-hand side. So 1 and negative 1, those are not equal. So for B, is it differentiable at x equals 0? That's a nope with an exclamation point you can't see. All right, kind of squeeze it in there. That's a no, okay? So even if it is continuous, it may not be differentiable. But in this section, what we're looking at is if it is differentiable, it will be continuous. Nice, huh? So based on our previous results, where we know that f of x is not differentiable at x equals 0, that means that it is differentiable everywhere else. So that means that f of x equaling the absolute value of x is differentiable when x can be any other number in its domain. Sorry for all the squeaking. So the contrapositive of the theorem, which is our next part of section 2.8, is that if f is not continuous at A, then f is not differentiable. So if it is continuous, we don't know if it's differentiable. But if it's not continuous, then it's definitely not differentiable. Okay, so there are three possibilities that a function fails to be differentiable. First of all, if the graph of f has a sharp corner at A, so for kind of like, well, I'm not going to draw it. If the graph of f has a sharp corner at x equals A, like an absolute value. If the function f is discontinuous at x equals A, like it's a piecewise function and there's a jump. Or if there's a vertical tangent line at x equals A. Let's see a couple examples of those. These three functions all do not have a tangent at x equals 1. Every single one of these. This might be hard to see here. I don't know if you can, but this is supposed to be 2/3, so to the 2/3 power. All right, so let's look at this. This graph right here, if you see, has a sharp corner or like a cusp. Okay, so it's not really a corner, but more like a cusp, but it's got a sharpness to it. It is differentiable at every other value other than x equals 1. This next graph here, if I graph the x squared minus 1 and then negative x plus 2, there's a jump here. So I cannot find the derivative for x equals 1. And then this function right here, the cube root of 2 times the cube root of x minus 1 has what's a vertical tangent line. And so this is not differentiable at x equals 1 either. These are the three things, okay? Remember, sharp corner, a discontinuity, or a vertical tangent. Those are the three things where you cannot find the derivative. It doesn't mean you can't find the derivative at the other points. You most definitely can. You just can't find the derivative at those particular values. Next section, higher derivatives. So I don't just want to look at the first derivative. Sometimes I need to take a few derivatives. Okay, if you've got y as f of x as a differentiable function, then the derivative y prime is equal to f prime of x is itself a function as well. In this context then, y prime is the first derivative. And if we differentiate that y prime, again, we get the second derivative. We denote the second derivative by taking the prime of y prime and writing it as y double prime. Or we take the prime of f prime of x and we get f double prime of x. You see? Now remember, there's a crap ton of notation for derivatives, so we want to have a way to find out what all the notations are. So let's look at the first one. The prime notation's one of the nicer ones. So you got first derivative, second derivative with 2 little primes, 3 derivatives with 4 little primes. Once you get to fourth derivative, notice that we're not using the little dashes anymore. We're using parentheses and then the number 4. And then if we're finding the nth derivative, which means the derivative n times, we have to use parentheses n. It's similar for f prime of x. Again, second derivative has 2 primes. Third derivative has 3 primes. Fourth derivative, parentheses 4. Nth derivative, parentheses n. Now let's look at Leibniz notations. Now Leibniz was a guy that was working on calculus around the same time as Isaac Newton, but I believe that Isaac Newton published first. I can't remember. There was a big old math smackdown where they were claiming that they stole it from each other. It was drama in the 1600s. But either way, Leibniz also did some stuff, and we use his notation. So remember this from previously. If I have a dy dx, and I want to write the second derivative, what I'm doing is I'm doing d squared y of dx squared. Or I'm doing d cubed y of dx cubed for the third derivative. Or d fourth y of dx to the fourth. Or for the nth derivative, dny over dx to the n. This one's a little interesting. Just kind of keep in mind what I'm doing each time is I am going to write it over here. I am taking the derivative with respect to x of whatever I took the derivative here. So if I take the derivative here, this is when I find the second derivative. Notice I take the derivative with respect to x of the first derivative. Well, that's why I get d squared and then dx squared. Notice that the y is never getting put to a power in the top. Just the d is. Okay? It's similar for the Leibniz notation for the function. Again, here's my fourth derivative of f of x. If I use this Leibniz notation, which you'll see, I think honestly when we use this the most is if you get into Calc 3. I don't see it a whole lot in Calc 1. But in Calc 3, here's the derivative with respect to x of f of x. And then here if you take the second derivative, the third derivative, the fourth, and the nth derivative. And then the idea is that no matter how many derivatives you're taking, you can write it in a different fashion. Recall in one of our previous examples, we found the derivative function for f of x. And we found this derivative function to be 3x squared minus 2. So let's find the second, third, and fourth derivative using the definition of a derivative. Again, remember, we're still doing it the long way. So we're going to take the derivative of the second derivative. Actually, I should write that first. So we are going to take the derivative of the first derivative, which is going to give me y prime. I'm going to take the derivative of 3x squared minus 2. So I'm going to do the limit as h approaches 0 of f of x plus h minus f of x all over h. Now, f of x plus h, if I plug this in here, is going to be 3 times x plus h squared minus 2. And then I'm going to subtract from that the regular f of x, which is minus 3x squared minus 2. Dang it, I forgot my limit function. That squeaking is very distracting to me. We're going to go to a different color, see if that helps. All right, so now... much better. So I'm going to square this, and I'm going to multiply that out by 3. So if I square x plus h squared, keep in mind that's going to give me x squared plus 2xh plus h squared. Darn it, it's still squeaky. And then I'm going to multiply the 3 out. Okay, then I need to multiply the 3 out. So I'm going to end up with 3x squared plus 6xh plus 3h squared, and then I'm going to subtract 2, and I'm going to distribute this negative sign here, so I've got minus 3x squared plus 2, and this is all over h. Notice something exciting happens. Okay, what happens? Well, my stuff that does not have an h cancels, right? So my 3x squared cancels. My 2 cancels. And then I'm left with 6xh plus 3h squared all over h. I can now factor 1 power of h out, and I end up with 6x plus 3h. As this h cancels the h here and cancels the h here, so I'm only left with that 1. And then when I plug in h equals 0, I end up with 6x. So y double prime is going to give me 6x. All right, let's do triple prime. So I'm going to take the derivative of y double prime, which is going to give me y triple prime. The third derivative is actually called a jerk. Did you know that? It's kind of a neat little thing. So I'm going to plug in, now in this case, I'm going to plug in x plus h, so 6x plus h minus 6x minus the original all over h. I'm going to distribute the 6 out, see if anybody cancels. Yes, bum ba da bum, cancels. And then notice that the h's cancel too. So I just end up with 6. So the third derivative of this function is equal to 6. That's right. So if anybody ever says to you, don't be a third derivative, they're making commentary about your behavior. And perhaps it's time to do some self-reflection. All right, we're going to squeeze this fourth derivative in the bottom. Okay, so the fourth derivative is where we're going to take the derivative of the third derivative. So notice, f of x plus h, there's no x in there. So this is just going to be 6. And then minus 6. And then that's going to be all over h. Now, even though there's not much work to do here, I want you to notice something. Ignoring the limit for a second, what's 0 cookies divided by h children going to give you? So I have h number of kids, and then I have 0 cookies. How many cookies is each kid going to get? That's right, nothing. Yeah. So it doesn't matter about that h equaling 0 in the denominator. That fourth derivative is going to give me 0. By the way, we are going to learn a different method to take the derivative that's a lot faster than this limit definition. But for the first unit and for the first test, we're using the limit definition of the derivative. So make sure you know your math smoke and mirrors. Make sure you know how to factor, you know how to combine terms, you know how to expand and multiply, combine common denominators, all that stuff. Calculus is a class where basically every single thing you've ever learned in a math class is used, right? Have you seen that yet? Yeah, I noticed that too the first time I took calculus. Okie dokie. I hope this lecture went well for you. Let me know if you have any questions and work on your homework.